Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'm continuing to work through a question that was sent through to me by a student from their recent complex numbers exam. So I recently worked through part 1 in a separate video, so if you haven't seen that, I'd encourage you to go take a look. Here I'll be looking at part 2, which tells us by expressing z to the n minus 1 as a product of factors, deduce that 1 minus omega times 1 minus omega squared and so on, times 1 minus omega to the n minus 1 is all equal to n. Alright, so for this part, as usual, I'll just start by writing out what we're being asked to show. So here we're being told to deduce that 1 minus omega times 1 minus omega squared and so on, up to 1 minus omega to the n minus 1 is equal to n. And as I kind of outlined in the video where I worked through part 1, underpinning all this is roots of unity and those concepts. So we're kind of looking at z to the n equals 1 as an equation, which then is more commonly considered as z to the n minus 1 equals 0. And then we kind of go from there to think about all the solutions. So if we know that the roots of this are 1, omega, omega squared, and so on, all the way up to omega to the n minus 1, there's always n roots, and 1 is included. Then the way we can write this, we can actually, kind of like what you've probably seen a long time ago in math when you were factorizing, say, quadratics or any kind of polynomial. If we know that these are the roots, then what we can say is that z to the n minus 1 can be written as z minus 1 times z minus omega times z minus omega squared and so on, all the way up to z minus omega to the n minus 1. If you take the difference between z, the variable you're concerned with, and each of the roots, if you were to expand this, you'd end up with z to the n minus 1, kind of what you started with. It's a way of factorizing. So from here, if I just bring over the z to the n minus 1, oh sorry, just the z minus 1, I'd get z to the n minus 1 on z minus 1 is equal to z minus omega squared, and so on, up to z minus omega to the n minus 1. And the reason I've thought to do that is because up in our kind of expression that we're trying to deduce, it's got in the brackets minus omega squared minus omega to the n minus 1. So I just wanted to be able to line that up. So to do that, I had to kind of get rid of this bit. So that's why I brought it over. And I might call this equation 1, because another way we can factorize z to the n minus 1, something we can note that hopefully you're familiar with, is z to the n minus 1, we can also just write as z minus 1 times 1 plus z squared and so on, up to z to the n minus 1. That's a very common way of just doing a simple factorization of a polynomial. Hopefully you've seen and used it before. If you haven't, if it's the first time you've ever seen this, one way to kind of test it is to just try expanding it and see what you get, because you get z plus z squared plus z cubed and so on up to z to the n, and then you'll be minus 1 minus z squared and so on up to minusing z to the n minus 1, and all the items will cancel and you'll just end up with z to the n minus 1. So it's definitely legit, and in our case it can help us because, again, I'm going to bring the z minus 1 over, so we can say z to the n minus 1 on z minus 1 is equal to 1 plus z squared and so on up to z to the n minus 1, and I might call that equation 2. And again, kind of like with part 1, whilst this is a roots of unity question, the key techniques being used here aren't the classic roots of unity techniques. Here I'm effectively using simultaneous equations, which is a a technique you would have learned many years before doing Extension 2 math. But it's all kind of wrapped up around the concepts of roots of unity. And you've got to understand what you're dealing with roots of unity and combine them with these other, I guess, more basic techniques or concepts. But so here we have two equations. They're both z to the n-1 or z-1, so I can equate them. Let's equate 1 and 2. So what will we get? We'll get z minus omega squared, and so on, up to z minus omega to the n-1 is equal to 1 plus z squared, and so on, up to z n-1. And hopefully you see here on the left-hand side, it's very similar to what we're being asked to deduce. And over here, I'm adding up n things, because it's 1 and then z up to z to the n-1, so that's n-1 items plus the 1 are n items. So I'm very close. All I need is for z to be 1. So let's just do that. Let's let z equal 1, because we know one of the roots of z to the n-1 is 1. So it's a valid thing to let z be 1. It's one of the solutions. So when we're thinking about that solution of z equals 1, when we make that substitution, we get 1 minus omega squared, and so on, up to 1 minus omega to the n-1 equals 1 plus 1 squared plus, and so on, up to 1 to the n-1. And as I mentioned, there's n items here. So if we add up 1 n times, we're just going to get n. Sonic boom! And that's what we're being asked to show. So that's how to do that question. That's how we deduce this result. It's kind of simultaneous equations, and then kind of noticing that you get pretty close, and if you just had z equals 1, then you're there, and we can let z equal 1, because that's one of the solutions. Now, there is a question that popped up in my mind as I was working through this, and maybe you noticed it too. I might just get my red pen out here, because it's to do with letting z equal 1. I mean, at first I'm like, sure, that's fine, because it's one of the solutions, why not? But then I had a moment of doubt, because in the two simultaneous equations that I've equated to get here, you may notice there's a z minus 1 in the denominator of both of them. So if I look at the specific case of z being equal to 1, we get a denominator of 0. And I just wonder, is that an issue for this process, for this proof here? Am I allowed to let z equals 1? I think there's arguments for both. I mean, it is a solution, so why not? And maybe you can say that once we've equated these two, taken this side and this side, then the left-hand side is it's disappeared. It's not relevant anymore. So we're not really doing the left-hand side bit, so we don't need to worry. Possibly that's an argument. I genuinely don't know. I'd be interested to know your thoughts. If there's anyone out there watching this who has particular thoughts on whether this is an issue with the approach I've taken, please let me know. I can't personally think of any other way to get this result without letting z equal 1. But if there is a way, please let me know. Feel free to share, and I could maybe record a postscript to this outlining the alternative technique. But I think what I've just worked through is valid. I think it would hopefully get you the marks, maybe not, if not all the marks, at least some of the marks for this question. But there is this lingering doubt, is this okay? I think so, but I'm not 100% confident, so I would be interested in any thoughts. If you did find this explanation helpful, please be sure to give it a like. And if you're the kind of person who wants to keep their finger on the pulse with the kinds of questions other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. All right, tick boom.